We now present a lecture by Toby Cambray, delivered during the 5th ERBE Seminar event in January 2025 on the topic of mechanical cooling and dehumidification in the tropics. Toby Cambray is a doctoral researcher at UCL within the ERBE Centre for Doctoral Training, investigating how water-repellent surface treatments affect solid wall performance in retrofit applications. Prior to this, Toby acted as a founding director at GreenGauge, leading the building physics team. Here, he sought to bridge research and practice by applying advanced building physics to improve moisture management in retrofitting projects. Toby also contributes to Passivhaus Plus and the AECB expert panel, sharing his insights and expertise. This lecture was delivered during the 5th ERBE Seminar event, a series designed to spark critical discussions around building and energy. Co-organised by the ERBE Centre for Doctoral Training and the CIBSE Young Energy Performance Group, the series has covered topics such as test house monitoring, household readiness for heat pumps, and global energy supply logistics for net zero. Please do support the series and attend a future event, either online or in person. And without further ado, Toby's lecture will begin.
I'm Toby. I have a number of hats. I'm actually a student in ERBE, but also run a small consultancy practice down in Bath, and been doing Passivhaus design for a long time. Andy asked me if I could help out with this very interesting project. I can cut down, so I'll sort of skip over some of these details. But I've already seen the details for House 5, which I did some simulation work on. Well, simulation is a bit of a strong term, perhaps, but some investigation with some basic calculations to see essentially what we could do to retrofit the building in this kind of scenario that has been mentioned in terms of future climate change and getting hotter, and cultural changes in terms of increased uptake and sort of aspirations for air conditioning, and how can we do all that in the most sort of efficient way. This is the plan for House 5, and we were essentially looking at the idea of providing active cooling to the bedroom areas. So the kind of living area would remain naturally ventilated, and provide the ability to kind of actively cool the bedroom areas to make sure the children there can sleep better and have a cool refuge for sort of heat waves and that sort of thing. The whole building as it stands was designed around passive principles, so natural ventilation principles. So I've got the large windows and natural ventilation. So it's really about how can we start to sort of change some of those features to make it ready for cooling. What would that look like under an ideal scenario? What's kind of possible, given the various kind of constraints in terms of locally available materials and mechanical systems. I used PHPP, the Passivhaus planning package, as a simple kind of tool to start to understand that energy demand and how we can minimise it, and where can we make the most difference to improving the performance of the building in terms of comfort, given all of those kind of complexities around thermal comfort in this kind of context, and obviously the energy demand. Can we start to work towards some heuristics and pattern language of features that are going to help achieve these things. We're thinking about this idea of kind of having cool refuges, potentially different zones in house, so areas that remain naturally ventilated, these retreat areas, and then some mechanically conditioned spaces. I just wanted to kind of get this in here at this stage, just to kind of define some terms. So again, it's a bit of a spoiler, but it turns out in Tanzania, it's part of Tanzania at least, the dehumidification and the humidity is really important when we start thinking about active cooling. So just to make sure everyone's kind of aware of some of these terms, if I'm talking about sensible cooling, that's basically a change in the temperature of air generally. And if we're talking about latent heat or latent cooling, then that's to do with the energy associated with changing water between its liquid and vapor state. Yeah. So it turns out in this kind of climate, as we've already kind of touched on, the humidity is really important for thermal comfort as well as the temperature, which is a bit different to a UK context. And we've talked a lot already about the different thermal comfort models, but with sort of certain assumptions, then we can see that in this, so this is roughly a kind of typical outdoor ambient condition in village, and if we want to move towards more comfortable conditions, then we need to do quite a lot of dehumidification. So this is a psychrometric chart. So essentially we've got the amount of water in the air up the sort of y-axis here, and the temperature. So if we were to do purely sensible cooling, so just cooling the air down, as we sort of think about it, maybe in the UK context, we'd basically increase humidity pretty quickly and get condensation, and end up with slightly cooler but still very saturated air, which isn't actually going to be very comfortable. So we need to do some dehumidification as well to get towards to actually make a big difference to the thermal comfort. And also, so my research in ERBE is about retrofitting and things like mold risk, which is obviously a function of that humidity as well. So if we start getting to these very high levels of humidity, then we could have a risk of mold as well. So we want to make sure we're avoiding that. So yeah, if you go through the numbers, if we take a meter cube of air from 30 degrees, so basically these conditions here, if we take that meter cube of air, then we need to spend 0.66 watt hours on our sensible cooling, so just to change the temperature from 30 degrees C to 28. But to take that humidity out, so the moisture out of the air, to go from 88% down to 60, we need an awful lot more latent cooling, which is that much. So yeah, as I say, the latent cooling is really important, and we need to think very carefully about how we deal with that, both in terms of the fabric and the systems. So mainly talking about the fabric this afternoon. So that's sort of similar kind of information. So for this particular building, that's sort of the energy that we'd sort of end up needing. So 133 kilowatt-hours a square meter per year on the so that's mostly the latent energy. So that's getting on for 10 times as much as the Passivhaus criteria, and not that's necessarily a good point of reference, given that it's sort of designed for Western Europe and all the rest of it. But it's a pretty big number, and that's just for the air, before we start thinking about the solar gains and internal gains that we need to deal with via cooling as well, in order to generate these more comfortable conditions. And so to do that analysis, we sort of did a fair amount of work sort of figuring out things like what for this building at least, what was a sensible kind of moisture load that we can expect in that space for its particular use. So what kind of cooking is going on. That's mainly happening in different parts of the building. So sort of took that out. So this is actually quite a low moisture load, but even with that quite low moisture load, we have this pretty large latent load that we need to deal with, purely from tempering that incoming air. So there's been a lot of talk this afternoon about roofs. I won't sort of rehash that, but again, we looked at how that was the gains through the roof would impact on all that cooling. That's really important as well. So with PHP, it's a static model, so there's some kind of limitations around understanding things like diurnal differences in solar gain and re-radiation. So there's lots more kind of to unpack there, but these aren't really the best tools to do that. But yeah, there's some interesting additional kind of research that would be nice to get into there to understand all this better. But essentially, we've got a situation. We've got sun coming onto the roof during the day. Some of that's getting re-radiated. Some of it's warming up that roof, which will then pass on solar gain to the ceiling. So there's this kind of radiative effect kind of going on potentially as well, on top of which you aren't necessarily going to deal with by ventilation because it's just radiating from the roof covering onto the ceiling. So yeah, some interesting kind of stuff to unpack there, given what Ben was saying about the role of ceilings as well. So as Huda was saying, these small kind of differences in temperature can have a big difference, partly due to the way we perceive temperature as a function of air temperature and surface temperatures around us, the radiant temperature. So if we could start to even make what seems like kind of quite modest changes to these surface temperatures, that can have a pretty big impact on the thermal comfort. So you can again plot that on our psychrometric chart. With the difference in mean radiant temperature, the way this sort of works is we're essentially shunting the comfort bands from one side to the other as the mean radiant temperature changes, because this is the air temperature. So sort of it's a relative shift on those comfort bands. But yeah, that can have a non-significant impact on the difference in that comfort. So we've gone from the sort of slightly warm to the next band along, just by that sort of relatively modest change in the mean radiant temperature. And the other sort of elements kind of important there is the what we call radiant asymmetry. So essentially, if you've got a difference in radiant temperature between a ceiling and a floor, for example, then that can itself contribute to the thermal comfort or discomfort. So if we've got a hot ceiling specifically, then because of all the solar gain, then we get kind of double whammy. So that graph, we got time to delve into it, but that's sort of showing that kind of effect. So yeah, it's a really good idea to do as much as we can to protect that ceiling from solar gain. So one of the features that is pretty typical or central really in the UK for Passivhaus certification and design is MVHR. So hopefully that's something everyone's kind of familiar with. Something that we don't really think about in the UK is MVER, so E for energy or enthalpy. And so that's when we start thinking about recovering not just the heat, but the humidity or the kind of dryness, it turns out as well. We can do that. So enthalpy recovery is more common in very cold climates. So in Canada, for example, where we're heating up the air in the building relative to outside, and that dries it out in terms of relative humidity. So in order to kind of recover that energy, so that's the latent bit, in Canada we can recover the humidity from the outgoing airstream into the incoming what will be very dry air, and it turns out we can do basically the reverse in very humid climates. Essentially we have this sort of typically a plate heat exchanger in the MVHR. In the MVER, that plate heat exchanger has elements which are vapor permeable as well as being sort of thermally conductive. So with the PHP calculations, I sort of did a bit of hacking around to get this to work to start to understand the breakdown of where we're losing energy. So this was kind of the as-built version. So if we were to just stick mechanical cooling into the that house 5 in the bedrooms as they are, then we'd be using something like 300 kilowatt hours a square meter a year of energy to hit those design conditions all the time. So 20 degrees and 6% humidity, and yeah, we can sort of disaggregate kind of where that's sort of coming from. So a lot of it, where are we? Sorry, a lot of that energy is due to the need to dehumidify the air. So you're getting on for half of it, and that's as a result of the air that we have to bring in to provide ventilation to the place, but also the internal kind of release of moisture from breathing and stuff, and then the sort of the so beg pardon. So this would be sort of air due to infiltration. So we've made some assumptions about how leaky the building is at the moment, and then this would be the amount of dehumidification we provide to the mechanically ventilated air.
5-minute mark.
Thanks, Tom. Yeah, so we can kind of use this as a bit of a shopping list of things that we can try and do something about. So the heat losses or heat gains to the building from the warm air outside sort of passing heat inwards through the opaque elements is actually kind of really tiny. It's down here. So we've got quite a lot of opaque solar. So this is mainly that solar gain on the roof. So that's really important to do something about that as well. So between the roof sort of solar gains and the dehumidification, that's kind of our big wins for trying to reduce the energy performance of this building. So I've skipped a bunch of steps. Maybe we can go back and talk about this in a bit more detail at the end if we have time. But if we have our enthalpy recovery and a really good air tightness, so 0.6, which is what you need for Passivhaus certification, then we can make a pretty massive reduction in the dehumidification loads. So the scale's changed on here, but you can see that now the those internal gains, which are kind of fixed, and because we've got to breathe, we've got the same number of people in there, that they're a much bigger proportion, and the we've this sort of sky blue column, that's a lot smaller because we're doing our sort of enthalpy recovery, and this sort of pinky one's a lot less because we've made our building much more airtight, so we're not having to do dehumidification on all the air that's kind of leaking in. And we sort of had a bit of a stab at how much heat we'd be able to avoid coming into the building via the roof, and that's a bit of an imprecise one, because the physics is a bit more complicated than we can deal with directly in PHP, but it's a bit of a guess. So we can go from about 300 kilowatts per square meter a year down to 74, which is pretty big reduction. So that 74 kilowatt hours a year is still high, but this is a fairly kind of quick and dirty model. One of the kind of objectives here was just kind of get a high level understanding of how the building's working and how it can be made better. So this 74 is assuming that those bedrooms are conditioned 24/7, because it's a static model. So the sort of yeah, limitations on what we've done from that point of view, but yeah, it's sort of showing us the sort of direction of travel and the principles that we like to sort of think about. The other thing that Andy and Ben had kind of talked about is this. There's some interesting kind of issues around the benefits of radiative cooling at night, and those can't be very easily sort of represented in this kind of modelling, but that's okay. You know, we can build more complicated models or physical experiments and test those. This is just a different kind of perspective on things. So a couple of kind of key insights. The delta T, so the difference between air temperature indoors and outdoors, is lower in Tanzania than we have in the winter in the UK. So typically we heat to about 20 degrees in the UK. The winter average temperatures say like 5 or 10 degrees. Whereas we're maybe cooling to 28 and expecting average temperatures of the low 30s. So we've got that means our wall insulation and floor insulation are much less important in Tanzania. We've talked a lot about solar gains in the roof, and there's this humidity thing, which is really the kind of the big win if we can achieve it in this kind of climate. In this kind of climate where we've got this very high humidity, that basically means that we're going to really struggle to meet our Passivhaus criterion, even with pretty outstanding levels of air tightness and very efficient ventilation. Just the virtue of the fact that water takes a lot of energy to boil and condense means that we're never really going to be we're going to struggle to meet that Passivhaus criterion. But that's okay. It's not necessarily an appropriate target for this kind of building and this kind of region. And I think that's more or less it. So we're talking about the sort of the retrofit of House 5, but these principles apply to all buildings, new builds in Tanzania and other sort of hot, humid climates. It's about getting that ventilation and the air tightness right if we're going to do this active cooling. There's a whole bunch of other stuff around how we actually get mechanical systems to kind of do that, which it's another kind of can of worms, and sort of interesting supply chain and cultural issues around that, which we've got time to talk about. So I will leave it there.